the double replacement reaction. And remember that there were three types, one that forms a solid, a liquid, and a gas. Today we're specifically talking about precipitation reactions. So that's the double replacement where a solid is formed in the products, right? So we're gonna just need to know a couple of things for our precipitation reactions, and that is, you probably already know, but the difference between soluble and insoluble. And this is gonna help us determine whether or not the state symbol for a product is aqueous or solid, so AQ or S. If a product is soluble, that means it will dissolve. So it's gonna get the state symbol AQ. That means it's aqueous. If it will dissolve, right, if it will dissolve in water, it's aqueous. Insoluble means it will not dissolve, right? So it's not going to dissolve. That means it's going to have some form of solid, and so that is going to get the state symbol S because it's in the solid state, right? So that will be state symbol S. We're going to see that in these reactions here. So I'm going to walk us through one full example, looking at the state symbols here. So remember double replacement, we have two reactants, both that are compounds and both that are aqueous, and we form two compounds in the products, one that's aqueous and one that's solid. BaSO4, barium sulfate at the end, is our solid, right? So this is the full equation, equations that we've typically seen, right? Writing out the full equation. Now what we see in these reactions is that there are actually, when we break it down, there are ions that aren't participating in the reaction, all right? So if a compound is soluble and it's aqueous, it's going to dissolve. So we see Na2SO4, it's aqueous. That means it's going to dissolve. When it dissolves, it breaks down into its ions that make it up, right? Na2SO4 is made up of two sodium ions and one sulfate, SO4 ion. Okay, so that will break down into two Na pluses and one SO4 with a 2- charge. These are the ions that make this up, all right? So here we're writing the complete ionic equation. What ions is this actually breaking down into when it's dissolved? BaCl2, also aqueous, is also going to dissolve, which means it's going to break up into its ions. Ba with a 2+ charge and two chlorines, right? We have one Ba, and we know from the periodic table that barium has a 2+ charge, and we see two chlorines here. Two chlorines, and we know from the periodic table that chlorine has a 1- charge. Both of these are aqueous, so they get the state symbol aqueous. All right? When we look at our products over here, NaCl, we have two NaCls, also aqueous, right? So our product here is also dissolving, right? So it's also breaking up into its ions. Two Na+, aqueous, and we have two Cl's as well. So 2 Cl-, also aqueous. Now our last product is a solid. Remember, a solid means it's insoluble. It will not dissolve, right? If this is not dissolving, it's not breaking up into its ions. So we cannot break BaSO4 up into its ions because it can't dissolve. So we keep BaSO4 as a full compound right there, right? Because it is not breaking up into its ions. Now, this is a complete ionic equation for this reaction that's happening. When we're looking at chemistry, we actually look at what is going on overall. So what is actually not changing in the reaction? And that's the net ionic equation. It only includes ions that are participating in the reaction. That means ions that change in the reaction. If we look at this complete ionic equation, there are ions that don't change from the reactants to the products. All right, so if we're looking at this, we see two Na+ in the reactants, two Na+ in the products. This ion did not participate in the reaction. We also see Cl here. There's two Cl's in the reactants, two Cl- in the product. This ion did not change from the reactants to the products. So we're going to cross that out. It is not part of our net ionic equation because this only includes ions that participate in the reaction. Those two ions did not participate in the reaction. So what we're left with is SO4 2-, right here, Ba2+, right here, and they yield, right? So they're combining ultimately to form barium sulfate, BaSO4, which is a solid. Now, what happened to the sodium and the chlorine ions? They did not participate in the reaction. They're spectator ions. Think of a spectator not actually participating in a game. So we're left, our spectator ions do not participate in the reaction. If you look over there in that little bubble, it says the ions that are crossed out. What did we cross out? Na plus and Cl minus. So our two ions that did not participate, they're only spectating. They're watching the reaction happen ultimately. Na plus and Cl minus. All right? So that is how we break down our equations into net ionic equations. Now we're going to look at how we actually predict the products that are formed in these reactions.
Okay, so the way that we actually predict products of double replacement reactions is using the solubility rules, which are on the back of the periodic table. So the first thing that we do is we just end up switching the cations in our equation. So you're always going to be given the reactants, but you are just predicting the products. So first thing you're going to do is switch our cations. Remember, our cations always come first. They're positively charged. So switched our cations right here, you can see. And then the second step is to check if the products are soluble using our solubility rules. And the solubility rules are located on the back of the periodic table. You can see they're right here. And we just blew them up here so we can use them. There are 6 of them, and they are very straightforward and basic. You will always have them available to you. You don't have to memorize them or anything. And we're going to be practicing using them a lot in class and in our lab that we are doing. Remember that soluble is going to mean that we end up being aqueous as our state, and insoluble means that we have a solid. And our solubility rules have the word salt in here sometimes, and that just means an ionic compound, remember? So all of these right here are going to be salts because they're all different ionic compounds. So for our first example, we have nickel 2 nitrate and sodium carbonate yielding sodium nitrate and nickel 2 carbonate. Now often you will just be given this part, the beginning of the equation, just the reactants, and then you will be asked to write the names of the products. So that's the first thing you're going to do. Then you are actually going to write all the ions down, just similar to what Ms. Frankovic did on the last slide, because that's how we can figure out what the actual chemical formula is for each of them. So I started this already for you, but sodium is going to have a charge of +1, and our nitrate ion is going to be -1, so it's going to be, we crisscross and reduce, just as a reminder, this is how we predict. I would get sodium nitrate looking like this. For my second ionic compound that will form, I'm going to have nickel 2, nickel 2 is going to have a charge of 2+, and my carbonate ion is going to have a charge of 2-. This is something I would actually need to reduce, so I end up with 1 nickel ion and 1 carbonate ion in my second product. Now, the last thing I have to do is check using my solubility rules. So Ms. Frankovic actually has them. And as you can see, I'm going to use rule number 2, which is nitrates, chlorates, perchlorate, and acetate salts are soluble.
So in orange.
Nitrate is always going to be soluble no matter what it is with, no matter what cation it is creating a compound with. So this one is going to be aqueous. Second, I have my nickel carbonate, my nickel 2 carbonate, and you can see that's my 6th rule. Carbonates are insoluble except those with alkali metals and ammonium. This is neither an alkali metal or ammonium, it's a transition metal, so I am okay, and this is a solid. So this would be my cloudy precipitate that would form that you're going to see in our lab next week. Example 2 is going to be sodium sulfate and potassium acetate coming together to form, which you guys would predict this, but it is going to be sodium acetate.
Right, so sodium and potassium switch.
Yeah, sodium acetate and potassium sulfate. If you want to pause the video right here to go ahead and predict those, that would be a good idea because I'm going to speed it up. I don't want to use up too much time. But again, you would write down the ions and then you're going to predict the two products that would form. So the first product that would actually form is going to be, so pause right now and do that, is going to be sodium, which has a charge of 1+, sodium acetate. And then I'm going to leave this blank for now. And then my second is going to be potassium sulfate. And see it? Yes. SO4. Again, you shouldn't just guess at this. I just am a pro. I'm kidding. This is correct, right?
Yep.
Okay. So we're going to use our solubility rules again to predict. We're going to see sodium acetate. We're going to look what my acetate does.
Right here
That's
in orange.
again rule number 2. Acetate salts are soluble. That means
Always.
I am aqueous. And then my potassium sulfate, I'm also going to notice that sulfates are also soluble. Uh-oh.
Except
also,
with these ones.
Oh yeah, except with those, which none of those are potassium. So this is also aqueous. This is a big deal because this actually means that no reaction is happening. Nothing is forming. Those
We'll
are
see
all
why
just
in the next
ions.
slide too.
Yeah, all ions are just bobbing around.
It'll make more sense right now too. All right. So here are the two examples that Ms. Thomas just showed you. I'm going to go over the ionic, the complete ionic, and the net ionic equation for both of them. All right. So we already wrote this at the very top. You can rewrite it. But this is the same equation that she just did, the first one over there. When we break it down into the complete ionic, NiNO3 we have nickel with a 2+ charge, right? And nitrate with a minus charge. We have 2 nitrates, right? 2 nitrates. Both of them are aqueous. We have Na2CO3, which is breaking down into 2 NAs. So 2 NAs, sodium has a plus charge, and 1 CO3, 1 CO3. Carbonate has a 2- charge. Both are aqueous. Over there, NaNO3 is aqueous, so it's also breaking down into its ions, Na+, 2 of them, and 2 NO3s. Both of them are aqueous. Nickel carbonate is a solid. It cannot dissolve, it can't break into its ions, so we're keeping it as a compound there. So when we're looking at what hasn't changed here, and we're going to cross out the ions that remain the same, we see that NO3 is the same on both sides. So I'm going to cross those off and not fall. Na+, 2 Na pluses on both sides. So I'm going to cross those off. All right, so what are we left with? We have nickel 2+, which is aqueous. We're left with carbonate, which has a 2- charge. It's also aqueous. And our solid over there, NiCO3. Right, so that's what we're left with. Our spectator ions are the ones we crossed off. NO3 and Na. Right? Our last example, which is the same one that Ms. Thomas did, if we break it down into the complete ionic, all of these are aqueous. Every single one of those compounds. So every single one is breaking down into its ions. 2 sodiums, 1 sulfate. All right, make sure they have the charges on them because these are ions. These are the complete ionic equation. 2 potassium acetates break down into 2 potassiums and 2 acetates. Right, each acetate has a minus charge. Sodium acetate, there's 2 of them, break down into 2 sodiums, 2 acetates, +1 and -1 charge. Oops, -1. And potassium sulfate is aqueous. It's breaking down into potassium and sulfate ions. All right. Now, if we're looking at this, what hasn't changed? We're going to cross off the ions that haven't changed. Well, Na hasn't changed. SO4 is here. We cross off SO4. SO4 has not changed. There's 2 K pluses here. 2 K pluses on the products. That hasn't changed. 2 acetates. 2 acetates. Everything is crossed off. This is why no reaction happened. We've crossed off all the ions. All of the ions then are spectator ions. So we would write Na+, nope, oh yeah, SO4, 2-, C2H3O2 with a minus charge, and K+. All of them are spectator ions.